Okay, AP Physics 1, I'm going to take a look at worksheet 8 here. Kind of go through the beginning of this for you. I might assign a couple of these, but we'll see. For now, I'm just going to mostly talk conceptual on worksheet 8. So, really questions 1 through 5 are going to kind of drive my discussion. So, in the E-field lab, you guys made the 2 lines of charge. All right. I don't remember. Maybe this side was positive. It's usually how we do it. Negative on this side. Right? So 2 lines of charge, and we saw all the arrows in the middle kind of going across. And you guys did a nice job with this. It was cool. And then here we saw them coming in, and then most of you noted that they faded away as you got towards the outside edges of the board, right? And they kind of curved around in here a little bit. Or wait, those arrowheads are all going the wrong way. And they kind of curved around on the outside and faded away, right? Something like that. So the way we usually draw this is not with individual charges. We call that the parallel plate configuration, either 2 lines of charge or 2 parallel plates. So plate is if you made it like 2-dimensional, right? So if you had, you had one plate like this, one plate like this. Let's say this one was positive, this one was negative. You'd have field lines going from positive to negative. And we do this in the lab. I actually attach it to a charge source, so to speak, a positive and negative charge source. And I charge up 2 plates, and I put a little ball between them, and the ball will bounce back and forth between the 2 plates if I get the plates charged up nicely. So what we have on this worksheet are 2 parallel plates drawn the way that the Regents usually draws them. Usually draw them as these big chunky rectangles. Right? Let me fix that one a little bit. These big chunky rectangles where one of them has a positive charge accumulated on its surface. It must have gotten charged by having electrons removed from it, and perhaps those electrons were moved to this plate, causing this plate to be charged negatively. The field from this, between the 2 plates, right? I'm going to ignore outside of the 2 plates for now. That ends up, the field lines kind of start curving as you get to the outside. Kind of like almost ends up looking like a hamburger or something, right? They start curving, they go from positive to negative and so on, but I'm going to kind of ignore that. In fact, I'm going to get rid of those 2 curved ones. Note that the field will go all around it, and it will get weaker as you get farther away from the plates. Let me lock my focus here real quick. Sorry about that. So the first question says, what would happen if an electron were placed somewhere between the plates? In what direction would it experience a force and move? So if I put an electron, let's say right here, E minus, little negative charge, it's going to get attracted towards the top plate. It's actually going to start to accelerate immediately. It's going to experience a force upwards and go that way. It's going to get repelled from the bottom plate, attracted to the top plate. And actually, it's going to be a nice constant force. Remember, force equals QE. And this is the key to a parallel plate. This field is uniform. That's the word we use in physics. It's a uniform electric field. The lines are all parallel to each other, right? So it's a nice constant electric field. Maybe it's 10,000 newtons per coulomb or something. And we do this all the time in electronic devices, like in a lab setting, where we have a parallel plate configuration. One's positive, one's negative. It's used all the time in manufacturing of electronic devices, computer chips, all kinds of things. Particle accelerators, not something you normally come across, but we use them a lot. Capacitors. There's something called a capacitor, which is in every single electronic device you own for the most part. And they are a parallel plate configuration at the end of the day. And put into a circuit, which is pretty cool, has some pretty cool uses. So anyway, this field is uniform. So therefore, the force, if the field is uniform, this means it's just kind of like another way to say constant. it's a constant field or uniform field between the plates. So if the field's uniform, the force must be constant. So we get a nice constant acceleration upwards. It's almost like if you were to drop a ball, right? And rather than falling down, it started to accelerate up into the sky, which is kind of interesting to think about. So if you had a positive charge and you released it here, number 3 there says, if you released a proton here, it would do the same thing, but it would look more like a ball falling down. So remember, positive charges move with the field, negative charges move against the field naturally. If we took like a handful of electrons and protons and just dropped them in here, they'd automatically separate from each other. That may sound familiar to you. That's something we see. If you separate ions, we can use electric fields to rip apart ionic molecules, so to speak. Salt. We can rip apart any molecule really with an electric field, which is important thing to think about. Electrolysis and such. Anyway, so number 4 is a cool question, all right? So this is where we start to get into the bending of a beam of ions, all right? And I guarantee you there's somebody in this class who in college will do research in a lab where you have a beam of ions that needs to be bent. Somebody will, guaranteed, in your class, either Physics 11H or even AP Physics 1 maybe. Somebody will do that because, I encountered it many times in college in various lab settings as an engineering major and then a physics major. But anyhow, what if an electron were shot into the middle of the plates horizontally from the left? So this is a little bit different of a question here. We shot an electron. How the heck do you shoot an electron? Well, you use an electric field. You use something called an electron gun, which I'll attempt to explain to you a little later on. I'll explain the electron gun after I kind of talk about this. So if you shot an electron in horizontally, so you took this parallel plate configuration, you sealed it up in a nice vacuum chamber, pumped out all the gas, and you could somehow shoot an electron out of a little gun, right? We usually draw them like this. Electron gun, right? And you could shoot it out of there, let's say somehow. And here it goes. What would happen when it hit this field? As soon as it hit this field, its path would bend upwards towards the plate. And if it's going fast enough, it'd actually pass through and, maybe end up hitting somewhere over here at the end of your device or something. So it would actually look like a ball that was thrown, projectile motion, but rather than falling towards the ground, it would fall or get attracted towards the positive plate. You twist it into a circle. All right. Number 4, how about a proton? Well, if I could somehow have a proton gun and I shot it in there, it would do the same thing, but it would bend downwards. And in fact, what you learn is the deflection angle, which is like kind of this angle. The deflection angle is greater for an electron because it has less mass, right? They both experience the same force, F equals QE, right? F equals QE. So both the electron and the proton experience the same force when they enter this field. All right. Equals MA. So the bigger the mass, the harder it is for that field to pull it down. They have the same amount of charge, electron and proton, same magnitude of charge. They experience the same magnitude of force from the field. But because the proton has a bigger mass, the effect on the proton in deflecting it is not as much as the electron. Pretty cool stuff there. That was one that would be asked conceptually. That's something I could ask you on the final or on a quiz or something, show you this drawing and, an electron is shot in there, and then I could say, okay, where on the screen to the right is it going to hit? And I could say like A, B, C, and maybe like D is, I don't know, doesn't hit or something. I don't know. But anyhow, so there we go. The electric field acts a lot like the gravitational field. It can accelerate things. Just like with gravity, if I lift something up against gravity, right, and I then release it, the object will gain kinetic energy. So if I put energy into an object, right, and I lift it up off the ground, right, then I release it, the object will fall back down and it'll gain kinetic energy. Well, it's the same thing with an electric field. If I put a charge in an electric field and release it, the electric field will accelerate it, like we saw in the last worksheet here. And we said work done by the field is the force of the field over the distance, right? So if we have some electric field, I'm going to draw it like number 6 here. All right, we've got some electric field pointing straight down. That's our electric field. You know, maybe it's a positive plate up here, negative plate down here. And we take some little charge, right, and we let the field move it over a distance of 1/2 meter, right? It's going to start off at rest, and by the time it gets down here, it's going to have gained kinetic energy. If I made an energy bar diagram of this, it's kind of cool to think about. I'd have PE, not G. It would actually be electric potential energy, and KE. PE, E, and KE. All right, let's say I started off, I released it right here to have a bunch of electrical potential energy, no kinetic. I let it go, it'll start gaining kinetic energy, right? So the potential energy due to electric field would go down, the kinetic energy would go up. Eventually, when it hits the negative plate, let's say it's a little positive charge, then you've used up all the electric potential energy. So it's kind of, I will draw the plates in here, right? It's kind of cool. I release it up here. The closer I release it to the positive plate, the more distance it has to move, therefore the more energy it'll gain. All right, so that's pretty cool. Pretty cool. So you could actually make kind of a potential energy, electric potential energy equation too, if you wanted to, but that's, you know, a little bit beyond what we're doing here. So the force that's acting on it, right, I'm going to redraw it over here to get us kind of a, you know, there's that little charge Q, right? There's the force acting on it. Force equals Q, and this is the electric field, E, QE. So I'll put that in here, QE, times whatever distance you move it over. All right, so these problems are pretty basic. Number 6 says 2,000 Newton per Coulomb. Electric field moves a 0.02 Coulomb charge, 0.05 meters straight down. How much work has it done? Well, work, all right, 0.02 coulombs. Electric field, 2,000 Newtons per Coulomb. And a distance of 0.5 meters. All right, so we can go ahead and solve that. 0.02 times 2,000 times 0.5. That gives us a work of 20. Let's see, what are the units here? Coulombs cancel. I end up with newtons times meters. Holy cow, that's joules. 20 joules. So that charge will have gained 20 joules of kinetic energy. Now I didn't ask you for the velocity. I didn't give you the mass. If I gave you the mass, you could then say, okay, 1/2 mv squared. Mass, if this was a 1 kilogram object, you know, we'd have 40 pi by 1 square root of that, you know, so we'd have, we could get the mass, we could get the velocity that way. So that's kind of cool. All right, so that's pretty much it for this. Let's see. We end up with this thing with the work QE times D, right? E times D. If I have a field, just kind of random field, electric field strength, and there's some distance here, no matter what charge I put here, it could be a big charge, little charge, whatever charge I put here, the E times D product here, put this arrow over here, the E times D product is the same for all of these, right? Any charge I put here, Q1, Q2, ... any charge I put here is going to have the same electric field strength multiplied by distance moving, right? So in that last problem, 2,000 newtons per coulomb times 0.5 meters. So what we have is 1,000 joules per coulomb of energy available in this field over this distance, right? So this we give a name. We call that electric potential difference, or change in voltage, which I ran out of space here. I'm off the screen and blah, blah, blah. So this E times D product, we ignore actually putting a charge in there, right? We just say, okay, we have this electric field. We're going to move something a certain distance. It could pick up, if I put something there, it's going to pick up 100 joules of potential, or 1,000 joules of potential energy per every coulomb of charge. So I place a 1 coulomb charged object in here. It's going to gain 1,000 joules of kinetic energy moving from here to here. If it's 1/10 of a coulomb, it's going to be 100 joules of kinetic energy, and so on, okay? So any charge I put in here, I can figure out how much kinetic energy it's going to change simply by multiplying the charge times the potential difference. So this is very useful, all right? Let me write this down. E times D, and in fact, we almost, in the regents, we almost never actually are given E and D. We're pretty much always just given what we call delta V, which is electric. And the regents does not put a delta there. I think that's a terrible move. Electric potential difference. Sometimes we just call it electric. Well, because the delta there is its difference. If it's just a V, technically it's just the electric potential relative to 0. It's the symbol. Or voltage difference. Or change in voltage. All right, so it becomes work equals Q delta V. All right, so you've seen voltages before. You probably haven't heard of electric potential difference, but you've seen voltages before. A 9-volt battery, a 1.5 volt battery, a 120 volt outlet in your house, a 12 volt is your car's battery, right? Your car, 12 volt adapter you need. Well, that's telling you that the potential difference from, for instance, a battery, right? Positive and negative side. If it's a 12 volt battery, that means the difference between the positive and negative side in terms of voltage is 12 volts. Or a charge, 1 coulomb of charge, could gain 12 joules per coulomb in moving from the positive side of the battery to the negative side of the battery. All right. So anyhow, that's just a background. I'm going to do more on this later on. Kind of running out of time here. That's it for tonight. This is a little bit long. I apologize for that. We'll see you guys later.